All right. Today's content is comfort and climate. So we'll tackle comfort first. And I know this is going to be pretty basic, and every one of us went through this in school, but this will be a good refresher. So, and what I will try to point out here is the things that are very important to us that we take for granted and we don't look at it closely. Okay? And I'm going to go back to science and basic 101 energy and stuff, so please bear with me if it's too much for you. Okay.
Crap, it's really cold over here.
Next week. It's all right.
Put on a sweater.
That's comfort.
An average North American adult. That's what ASHRAE is using as a default for determining comfort. And if you consider this as an adult, the first layer of comfort comes from skin, correct? And the second layer is clothing, and then the third layer is the building. So we'll talk about how these all three interact. And that's one of the reasons why we're designed, to make comfortable places, right? It's not the only reason, but that's one of the reasons. So we have to make sure that we understand that correctly. Okay? An average North American adult puts out heat energy equivalent to 2 50-watt bulbs. So just by having, 30 people here, it's equal to having 60 50-watt bulbs burning every hour. And this is under the seated conditions. If you're not doing a whole lot of exercise, at seated condition, everybody is putting equal to 100 watts every hour. We're putting this amount of energy. So imagine having a classroom with 30 kids. It will be slightly lower than 100 watts per kid, but still, it's a lot of energy to heat and cool, right? So that's one key thing that we need to understand. And then, how do we keep ourselves hot or cold within the body? Because the body the core of the body tries to maintain a temperature. Can anyone tell why?
Core of the body.
Survival.
Correct, it's survival. Because the organs within the core need to be in a certain temperature, otherwise we won't work. Correct?
We won't work.
We won't work as a system. But there are some inherent redundancies and within our system. For instance, the core of our body is very important to the body. Fingers, feet, not so important. So the comfort levels can go higher.
Tell that to
Priority.
a pianist.
Huh?
Tell that to a pianist.
So the comfort levels can go, we can stretch the comfort levels on the periphery of our body. And the core needs to be in a certain condition. And the majority of how we feel heat is through these three things: touch, blood, and water, right? Let's try to understand that. By touch, this sensation tells me if it's hot or cold. I either take heat or release heat, correct?
Right.
And the skin does that part. But how does the internal organs react to that? For instance, if the outside temperature, or in this room, let's say the temperature is too hot. Let's start with too cold. It's easier. Let's say it's too cold, right? Then what happens? My skin is where the first impact is, right? I'm going to start losing heat through my skin. So what happens if I continuously keep losing heat at the rate of 100 watts per hour, correct? That's how much heat I'm going to lose. If I keep losing that heat, what would happen to me? Yes, but the body won't let you have a brain, the body won't let us do that. So what the body will do is the internal core, it'll stop supplying blood and water to the periphery of the building. That's where the skin and all the toes and fingers, ears, nose, everything. Right, and that's why you get cold sooner on all those places first, before it gets to that. So the body's innate action should help us, the design philosophy, to somewhat, and that's what I'm trying to relate here. And then the second part is, when it's too hot outside, what happens?
Sweat.
Right, because we push more blood and more water out to the skin. But once you have moisture on the skin, just by evaporation, you can start cooling, right? So we talked about two things. When it's too cold, we shut down, we try to maintain the core. When it's too hot, we expand, and we try to release and try to cool ourselves out, right? And I'll make the analogy of why that's important when it comes to building at the end of this energy workshop, end of this week. So just keep that in mind. Blood, water, and touch are very important for the body. How do you take care of when it is too cold? How do you take care of that? Wrap yourself with clothing, correct?
Yep.
Thank you. And the next. Well, before we get into clothing, that's only one approach, right? Let's say I don't have access to clothing. What do I do?
Cuddle with your wife.
You turn the
Activity. Good point. Correct. Because then, huh?
Dial on the wall over there.
Dial on the wall. Oh, we're not going there yet. We're still trying to condition ourselves. Let's think about the building a little later. Correct. So if we're too cold, the two options. One, we either start doing exercise or something, because so our internal metabolic rate increases. We start pumping more heat, or we put on. We could, or we do we add more clothes, right? The metabolic rate is defined by this term called MET, M-E-T, and 1 MET is equal to 100 watts, roughly. A person seated, releasing about 100 watts. Can anyone tell why that's important? Why do we need to know MET? Okay, we design, let's say take a school building. Is everyone in the school always sitting?
No.
Okay. So we need to know what they're doing. Activity is very important. Gymnasiums, a lot different than a classroom. How do we provide comfort?
So Prem, how many METs are possible at the highest activity level?
Great question. 2 minutes down the road. Okay. So here's there are two problems, and again, forget that you are designing a building or heating and cooling or anything. This is just our body, right? There are two main problems for the core of the body. One, the outside temperature drops in temperature. That's a problem, or it rises in temperature. So what happens is there are 4 ways we conduct heat, or there is heat flow within our body, correct? And this is something that we've always learned: convection, conduction, radiation, and evaporation. When the temperature drops, what we do? Cuddle your wife. Conduction, that's what conduction is. Radiation, we go out on the sun. We get more sun. That's radiation. Convection, you know, explain convection? It's air closer to a hot body. So if there is a hot wall, you just go stand near it. So by convection, it starts to give you that warmth, right? And then lastly, that's with the problem when it is cold. When it is hot, evaporation, we go find a shade, right? Because we don't want direct radiation on us from the sun. Or direct conduction. We don't want direct conduction. We don't want convection. What we want is evaporation so that we cool off, right? So the answer to that is there is moving air. You turn. How many people use ceiling fans in your homes? Why don't we do that in our buildings?
Got to clean them, or spin around all the time, or wobbling.
Okay. Good question. You need to ask that to the owner, right?
Just hang on them.
Why don't we do that? Okay. All right. So going back to your question, John. Let's say, there is a problem in this. And this is where I'm going to try to get why we're designing buildings and why we're designing comfortable buildings. Us as human beings, we can try to do one of these things to keep ourselves comfortable within the core, but it only goes up to a certain limit. That limit is the clothing. Come on, how many layers of clothing can you have and just walk around? There is a limit.
There is a limit.
Yes, there is a limit, correct? And then, as far as metabolic rate, the highest you can go is 7. Okay, the highest metabolic rate is 7. That's when you're wrestling. You
Wrestling?
can't be wrestling all the time. Right? So,
Wrestling?
huh?
Yes.
Wrestling.
Wrestling, right? So 6 is normal human limit. Once you go to 6, that's it. Once you go to hit 6, that's it. You can't take any more.
I'm curious why you don't have food and water up here.
Food and water is a good one. It'll come pretty soon. Yeah, and that's another one.
That's week 3.
To keep yourself hot and cold. Correct. Good catch. So that's the limitation on keeping ourselves hot within the core. Yes.
You know, based on just the natural observation, when you see a bird, it's hot, opens up the wings.
Right.
In this reaction, how do you relate this to these 3 ways of either gaining or losing heat?
Correct. Good question. When the bird opens up its wings, it increases its surface area for evaporation. Correct.
Or convection?
Or convection. So there's multiple ways human beings deal with this, and other organisms deal with this.
Would you relate that to reducing the skin of the building also? You can control more heat gain?
That'll be on week 3.
If we run over, we're blaming you.
Show me what we have, Grim.
Dang it.
Okay. So what is the problem with on this side? On the when it's too hot, what's the limitation?
You can't always find shade and you can't always move the air.
Okay. Well, let's say you can.
Oh, okay.
Let's say you can move the air. What's the limitation? Can you guys see? Okay. Too windy. The problem is after a certain foot per minute, the amount of the speed at which the air moves, we can't deal with it. And that limit is 160 foot per minute. After that, you can't deal with that fast moving air.
It's not on your skin long enough to do any effect, right?
Right.
It moves fast.
It
so
also-
fast, it doesn't ever have a chance to transfer any heat or anything.
That's one reason. And then we just can't deal with that fast of air
Okay.
moving on us.
Sorry.
Windburn or
Ah,
My bad.
kind of like frostbite? You get windburn.
This is when you're like
it depends on the temperature, but we're talking about cooling here. So at 160 is the limit. So when we're designing our diffusers, what do we design our diffusers at?
50 feet per minute. 50 feet per minute at the person.
Right, and this is called draft. Because what happens is, if you're right below a diffuser, right, say like that, right, and that's coming at 150 foot per minute at you, can you guys comfortably stay here?
You feel it.
No, that's the problem. You can. Okay.
He's always radiating.
Is
He's all
is humidity, should that be listed
He's
as
the
a problem?
convection.
Or how you-
Humidity is
Week 4.
taken care of here.
Yeah, this week 4.
Humidity is taken care of there, in the evaporation, and in convection too. I think humidity plays a huge role when it comes to this condition. And humidity plays less of a role here. It's more of convection, conduction, radiation when it is too cold outside. Okay. So there is a limit as humans we can do to try to maintain ourselves, right? So then what are our solutions? We have the other 2 skins for us. One we have clothing, the other we have building. Before we go into building, well actually let's go into building. Clothing and building. What do you see? I mean, what's the problem? I mean, that seems pretty obvious, right? You put more clothes on, have a comfortable building, call it a day, everybody's comfortable, no complaints anywhere. What is the problem?
Can't take your building off.
You can, but the problem is the buildings and the clothing are not always reliable. Why? Because style dominates over comfort. Because I choose this shirt today, right?
Yeah.
And it's not always because of comfort. It is also because of style. And that happens with the buildings too. We don't always design buildings that are always comfortable. It's not.
Very good.
That's our problem, right? So us as designers, architects and engineers, our goal is to try to design buildings both that meet both style and comfort. So we'll see how.